Hey, good morning, everybody. Welcome to what I would like to say is your final installment for Chapter 1. Yeah, whole Chapter 1 in the bag. Well, not yet, but yeah, it's like this last bit before it's in the bag. All right, so listen. The last thing we talked about were electrons, and they seem to be some pretty trippy things. And one of the things that was said about electrons was that it's like the electrons are what make the chemical reactions happen, right? So most chemical reactions are electrons being shuffled around. So that seems to me that like electrons are kind of important then if they are what make all the chemical reactions, and this is chemistry. So I think that makes electrons kind of important. Also, we learned earlier that electrons can come and go, and then you make ions, right? If you lose electrons, you become like a positive ion. If you gain electrons, you become more negative. And when you change, you remember that demo thing that we did when we had like calcium and I put it in water and then it made a gas, right? But the calcium went from a metal that was silver, and in our case it was kind of chunky, and it went into like a white powder. So like that's when it lost electrons. So that's like a really big change, you know what I mean? So we need some way to keep track of electrons, because then we can know if it's an ion, if it's an atom. We know if it's positive, we know if it's negative, all kinds of good stuff can be learned. So this is what we're going to learn about today. Electron configuration. Electron configuration. Yes, absolutely. This is all it really means is keeping track of electrons. Why do we need to keep track of electrons? Everything I just said. Okay? So here is something that I want us to really dial in on. These things, valence electrons, because believe it or not all electrons are equal. Valence electrons are the electrons on the outermost energy level or shell. So one of the things we talked about were like how electrons are kind of layered, like they're like orbitals are like kind of layered like steps of a ladder or the floors of a building. Another way you can think about it is they make like layers of an onion. So you have your first layer, you have your second layer, you have your third layer, and in this case, also the nucleus is right here. So there's the nucleus, and so let's say on your third energy level we have 1, 2, 3 electrons. That means that this particular, and we're going to ignore everything inside. That means that this particular atom is going to have 3 valence electrons because there are 1, 2, 3 electrons on the outside, or that outermost energy level, or the outermost orbital. I guess there's a bunch of different ways you can like think about it. And why do we care about that? Well, valence electrons are like, they do a lot of stuff. They are pretty important because all the chemical and physical properties of an atom come from, you guessed it, the valence electrons. So we get the chemical properties from these valence electrons. Okay, so the way these atoms react totally depends on the valence electrons, because it is the valence electrons that enter into a chemical reaction. So if we come back up to this little atom here, we'll have 2 here, and 1, 2, 3, 4, 5, 6, 7, 8. These like this energy level 1, right? This first energy level here, it does not, like those electrons don't do anything. This guy here in energy level 2, all 8 of these electrons, they don't do anything. They just stay there. However, energy level 3, these are the electrons. Electron number 1, electron number 2, electron number 3. These are where those are the 3 electrons that actually do chemical reacting. The other ones don't really do anything. That's just kind of how it goes. And now this thing right here I want to talk about, where we cannot have more than 8 valence electrons. This is because we're in high school chemistry. So for us in this class, we are going to do no more than 8 valence electrons. And the reason being that once you hit 8 valence electrons, the atom is like super duper ultra crazy stable. It doesn't want to lose them, doesn't want to gain them. Pretty much sits nice and happy, you know what I'm saying? So we cannot have more than 8 because the atoms are the most stable with 8 valence electrons. Now, the reason why has a lot to do with the fact that Electrons are charged. They are like very, very small, and they behave in the quantum physics realm of behaviors. But basically, for us, for almost any chemist, the only reason we care about the 8 is because 8 is where it's stable. So once an atom has 8 valence electrons, it doesn't want to react anymore because 8 is really super stable. Every single electron is happy. And so, because 8 is what makes electrons happy, the atoms are going to gain or they are going to lose electrons so they can hit that magical 8, right? 8 is great. You remember that song when you were little? Like 3? 3 is the magic number. 3 is the magic number. No? Well, you should. You should look it up. It's an awesome, awesome song from like, I think it's Sesame Street back when I was little. So, you know, you'll have to hit the archives. Anyway, actually 8 is the magic number. This guy right here, 8 is the magic number. Why? Because 8 is great. There you go. And if you look at all the noble gases, these are the gases way, like if this is the periodic table, right? And then you got this long thing, and then you got this big old block here, and at the very end of the block, you've got this group, this group right here. This group is the noble gases. They don't react with anything. That's why they're called the noble gases. Completely what we call inert. No reactions, none whatsoever, because every single one of them, every single element all the way down this line has 8 valence electrons. Super duper stable. They love it. They're happy, so they don't care about anybody else. They don't react with this peasantry over here, all these people that don't have all 8 valence electrons. Anyway, so here's the deal. The title of these notes are called electron configuration, right? And there's actually a reason why we're calling it electron configuration. Because it shows us a couple of things that are going to be pretty important for understanding the behavior of atoms and how they interact with other atoms in a chemical reaction or just sort of in the world. So this electron configuration tells us like 2 really important things. It shows us how many energy levels, right? Or like layers of an onion or steps on the ladder or like floors on the building. How many layers of electrons? So it tells us how many energy levels an atom has and how many electrons are in each energy level. That's actually pretty important because this is it right here. It helps us predict the atom's behavior. In all of science, what we're trying to do is make predictions. So that if we have this set of circumstances, we expect this outcome. And if we change the circumstances just a little bit, we want to be able to predict and know what's going to happen. It's like a human thing. We love knowing what's going to happen. But also, it helps us do things like, you know, make cell phones and medicine and vaccinations and all kinds of crazy stuff. So let's just start at the very beginning here. We're going to start with fluorine and zinc. And here's how this electron configuration works. This is it right here. Okay, so this right here, this is your atomic symbol, right? That's F is for fluorine. This is the atomic number. That tells us the number of protons, and this is the electron configuration. And the way the electron configuration works is you want to think of it like right here is the nucleus, right? And then here's energy level 1, and here is energy level 2. Does it make sense? So you read it just like a sentence. You read it from left to right, so you read it this way. Like where you start is the inside, right? So we're starting here. That's our first energy level. We come out here, that's our second energy level, and so on and so forth, right? So this tells us that fluorine has how many layers? I'll let you think about it. How many energy levels? How many shells? 2 energy levels, right? So there are 2 energy levels, and we know that in the first energy level, we have 2 electrons. How many electrons are in the second energy level? 7. Dig? See how that works? Very nice. All right, let's come over here to zinc. Now remember, the way we read the electron configuration, which is that this like series of numbers underneath the atomic number, goes like this. Energy level 1, energy level 2, energy level 3, energy level 4. Let's do that again. Energy level 1, energy level 2, energy level 3, energy level 4. Right? Okay, so let's go through. There are 1, 2, 3, 4 energy levels. Does that make sense? There are 2 in the first, 8 in the second, 18 in the third, and 2 in the outside energy level. So the next question that I have for you guys is, how many valence electrons do we have in fluorine, and how many valence electrons do we have in zinc? Well, for fluorine, since this is, remember, I just erased it. I'm going to rebuild this. This is your first energy level. This is your second energy level. You see how this is your outer energy level, right? This is your outer energy level right here. So you have 7. You have 7 valence electrons in fluorine, which means that if you think about it, if it wants 8, fluorine needs to gather up 1 more. And if you look up here at the corner, that's exactly what fluorine does. When it turns into an ion, it has a -1 charge. Why? Because atoms gain and lose electrons to get 8, right? And so if fluorine is at 7, dude, he's like 1 away. So fluorine's going to be pretty serious about like grabbing and like trying to get that extra electron to get 8. So zinc. Here we go. Yep. So there's the nucleus. Here's energy level 1, energy level 2, energy level 3, energy level 4. How many valence electrons does zinc have? You bet 2 valence electrons, right? Yeah. So and 2 is much further away to 8 than to 0. So what happens is zinc will actually lose these 2 valence electrons and become a +2. Weird stuff, but there it is. So this is the electron configuration right here, right? The series of numbers underneath the atomic number. It tells us the number of shells and the number of electrons inside each shell. Amazing. So how many valence electrons are in the following? Well, let me see if I can help you out here. All right, this is going to help. Ooh, wait. There, that'll help. So the question is, let me come back over here. How many valence electrons are in the following? So we need to find oxygen here. Oh, there's oxygen right here. So how many valence electrons do we have? Well, if you look right here, this is my electron configuration. It looks like I have 2 in the first shell and 6 in the second shell. So I think that's going to tell me 6 valence electrons. Absolutely. Good job. I knew you guys had it in you. All right, so let's go to carbon. Oops. My bad, sorry. Let's go to carbon right here. So carbon has first 2, then 4. So that looks like how many valence electrons? Ooh. Yep. 4. Now let's go to silicone. And if you notice, silicone is right here. Silicone is right below carbon. And it also has 4 valence electrons. Well, that's pretty funny if you take a minute. Think about this for a minute. If the valence electrons give atoms their chemical properties, and these both have the exact same number of valence electrons, you'd think that they act kind of similar, you know? Well, they do. Actually, carbon and silicone actually act very, very similar. All right, let's check this one out. Magnesium. Where in the heck is magnesium? Well, oh, there it is. It's right here. 2, 8, 2. All right, so it looks like 2 in the first shell, 8 in the second shell, 2 in the outermost third shell. This thing is easy. This thing is 2. Now let's turn it up a little bit because I want you to look close at the details, right? There are some times when you have to sweat the details. You see this right here? You see this? That is a charge, and we've talked about this before, right? That happens because an atom gains or loses electrons. So if it's positive, that means negatively charged electrons are leaving. And if it's +1, that means that 1 has left. So I want you to lock that into your brain while we come over here and check out sodium. So sodium is 281. All right, so sodium is 2-8-1. But if you look at this, that says it has just lost one valence electron, right? So let's go like this. Okay, it lost its valence electron. So how many valence electrons does sodium with a +1 charge have? None. Zero. Zip, zilch, nada. So when atoms lose electrons and they become an ion, for us in this class, we're going to just go with like the first easy step and say they will have 0 valence electrons because they lose the valence electron. So look at this, right? So here's sodium in its regular normal condition. It's like an element. But look, when it loses that valence electron and becomes an ion, dude, are you seeing this? Right? There's that 8, and so sodium loses that outer electron so that it has this super stable like iron shell of 8 electrons showing out to the world because that's really, really stable. So that's why it does it. That's why sodium is almost always an ion, because it needs to get rid of that 1 valence electron. So now it has 0 valence electrons because it lost its electron. So it shows 8. Shows 8 to the world to be super stable. Dig? Dug. Great. Next, the electron configuration can be used to help us keep track of excited electrons. So look, here's the deal. If you remember, excited state means that the electron has gone from its normal state, or the ground state, it jumped up a level because it gained energy for whatever reason. So what we've got here is we have calcium in the ground state, 2 in the first, 8 in the second, 8 in the third, 2 in the fourth. So the only thing that excited state means is that electrons jump up. That's it. Oh, one other thing that we should talk about with like this electron configuration. When you pour water into a glass, how does it fill? Does it fill from the top to the bottom, or does it fill from the bottom up? You know, right? It's kind of that. It's kind of the same kind of thing here with electrons. When we add electrons to an atom, it fills from the bottom shell out. All right? So for calcium to have 2 in its, if that's its valence shell, that means this first one is full. This is full, and then this one is full. Full. They are all full, and then so as we're adding electrons, it would be up in this shell where things are being added. Do you understand what I'm saying? So what that means is you can't add electrons here. So you can't take an electron from like the first energy level and like boop, pop it up into that one. That just doesn't work because this level, that shell, is full. So it just can't do. So the easiest way to show an excited state is you take 1 electron from the outermost shell and you jump it up to the next layer or the next rung of the ladder or the next floor of the building. And if I do this, I end up with an electron configuration that says 288-1-1 because 1 electron from the 4th energy level has jumped up into the 5th energy level. Right? Now remember, it only stays there for the blink of an eye, and it goes right back down to 2882 like regular calcium, and that's that. Or, and because like there's in nature it's never like, oh, this is the only way it ever happens. There's always more than one way that things can happen. So again, because that outer level, this level right here, it's not full. The valence shell, if it's not 8, it's not full for us, like for for Regents Chem 101. So what we can do is we can take an electron from the 3rd shell, whoop, and bump it up here. And then when we do that, we get this electron configuration. Does that make sense? So if you see this, it means that calcium lost an electron from the 3rd because it has jumped up into the 4th. So I'm going to clean this up, and I want us to look at a couple of like similarities, a couple of differences. I want us to see the patterns, right? The patterns here. All All right, so the first thing I want to do is count these up. That's 16, 17, 18, 19, 20. There are 20 electrons here, right? This is the ground state. This is the way we always find calcium normally. Now let's come down here to this excited state, and let's count up the electrons. That's 10, 18, 19, 20. Right? All right. Because it's still a calcium atom. Awesome. Now let's check out this one. That's 2 and 8 is 10, 17, 18, 19, 20. All right. Do you see that in each excited state electron configuration we have the same number of electrons? Because we haven't gained and we haven't lost. That's when we turn, that's like ion, that's when you become an ion, right? No electrons are being gained or lost here. Calcium, calcium has an atomic number of 20. So it has to have 20 electrons to remain a calcium atom. You dig? You understand what I'm saying? So if I have any number other than 20 for my electrons in my excited state, that's not the excited state electron configuration for calcium, because calcium has to have 20. Do you guys see that? What I want you to see, what's similar is the number of electrons, right? 20, 20, 20, 20, 20, 20. Everybody's got 20. But what's different is how those 20 are arranged. And here it is different because one got bumped out here, and here it is different because one got bumped out here. And the only other thing that we need to keep in mind when we think about electron configuration is that the bottom layers are full, just like pouring milk into a cup. Okay? Let's do lead. PB. Right there. Oh, gosh. 1832, 1804. 1832, 1804. 1832, 1804. Oh, a little side detail. Do you see on lead, right here, this little dash line right here, right? See that little dash? That means that there's more to that electron configuration, but they just couldn't fit it on there. All right? And so, to do an excited state, oh, there's my dash. I'm going to keep it simple here, guys. 18, 32, 18. Those guys are all full. Now my valence shell in the ground state has 4, so I'm going to take 1 out of there and just bump it up. Gosh, that was easy, right? You just take 1 electron, bump it up. That's it. Let's do this next one, nickel. There it is. 2, 8, 16, 2. That's something I can remember. 2, 8, 16, 2. Awesome. So if we're going to do an excited state, I'm going to do just like I did before. I'm going to keep it simple. I'm going to take 1 from the outermost and bump it up. But I could if I wanted. If I want to be super fancy. And you see, I took something from the 3rd energy level and bumped it out to the 4th. So both of those are totally legit. Totally fine. Here's something that is not okay. If I did 2, 7, 17, 2. No, can't do that, right? Because these bottom layers, these are full. So we can take something out and put it into this outer layer that is not full, but we cannot take something and we can't add more to that layer because they're full, right? There's actually quite literally, physically, no more space for electrons. Okay, that's awesome. Now, there is one last thing called Lewis electron dot diagrams. I know that you've seen these before in all your other science classes, but it's very simple. It is a method of keeping track of electrons. And here's how we do it. First, you got to determine the number of valence electrons. I think you can do that. Then you write the symbol and then 1 dot for each electron. Boop, boop. So there, that's it. Typically, the first 2 dots go together at 12 o'clock. I'm not going to hold you to it because it's a weird holdover. You can dig into it if you take Chem 101. But for us, we'll just say, like, you put the first 2 up top generally. So hydrogen has 1 valence electron. So we write H for hydrogen, boop, give it 1 dot. Helium is next, so we write He for helium. And if you look at the reference table, helium has 2 valence electrons. Boop, boop. Next is nitrogen. we go N is for nitrogen, but now I'm going to start insisting that we do it this way. There are 4 locations for electrons: north, south, east, and west. I don't know if that's east and west for you guys, but it is for me. So here's the thing. You have to fill them like, it's kind of like people getting on a bus. You have to put 1 electron in each spot first before you double up. So the way that I would draw the nitrogen is I will go, there's my nitrogen. And nitrogen has 5 valence electrons, right? So I would go 1, 2, 3, 4. That's what I mean, right? So there's north, south, east, west. There are 4 spots for electrons. So first we fill all the spots first, and then we start doubling up. 5. So that's how nitrogen looks like this, right? First, second, third, fourth, fifth. Same thing for oxygen. Oxygen has 6 valence electrons. So first I draw O for oxygen, and then we do our 6 valence electrons. 1, 2, 3, 4, 5, 6, right? Because you got to fill up the seats first with singles, right? It's literally like people getting on the bus. Nobody wants to crowd up next to some stranger. Okay, so you go 1, 2, 3, 4. Now we start doubling up. 5, 6, and it is very important that you follow that pattern. It doesn't matter where you start. You just have to go around in a circle. So I could start here and go 1, 2, 3, 4, 5, 6. There, see, I've got like a double electrons here, and single electrons here and here. So these two things are exactly the same. They're just like rotated a little bit, right? They're just like spun. So that's that. And that's really important to do that. And we're gonna because this is gonna help predict the structure of molecules when the atoms start to get together. So hold on to that. It'll come very clear later on why we have to go 1, 2, 3, 4, 5, 6, 7, 8. It has to go in that way. Why? Because there are 4 spots for electrons. Why are there only 4 spots for electrons? Because nature. We'll leave it at that for right now. Dig into Chem 101 and bonding. Actually, that's Chem 2, college level Chem 2. Dig into exactly why that is. And even then, there's a lot of stuff that we're like, oh, we'll ignore that. That's for physics. So, I mean, man, science is a deep dive. It's like forever learning. Okay, so helium. Helium has 2 valence electrons. So we go 1, 2. That's it. That's easy. Carbon. Carbon has 4 valence electrons. 2, that's helium. So this guy here is going to have 4. So just as always, we're going to start somewhere and go all the way around. Here, that's what that one looks like. The next one, fluorine. Fluorine has 7. So we're going to go 1, 2, 3, 4, 5, 6, 7. And again, like you can start anywhere. It doesn't really matter. Now sulfur. Sulfur has. Wait, actually, let me check. How many does sulfur have? I think it's 6. Yep, 6 valence electrons. See, you don't have to memorize stuff. 6 valence electrons. 1, 2, 3, 4, 5, 6. Whoa, look at that. These sulfur and oxygen. These two guys look really similar, right? And actually, fun fact, they do behave very, very similarly. And we have found at the bottom of the ocean in these volcanic, like places where there's like volcanoes under the ocean spewing like boiling hot water with like tons and tons of sulfur, enough to kill like we wouldn't live, man. We would all be dead. But there's so much sulfur in that water from the volcano erupting. There are little critters down there who have evolved to breathe with sulfur instead of oxygen. But do you see how sulfur and oxygen look almost exactly the same? 6 valence electrons, 6 valence electrons. These little critters, these little shrimps and the tube worms have been able to like harness sulfur to breathe, to do the work of oxygen inside their body. It's crazy, man. This universe, I'm telling you, the universe is weird. It's amazing too. Like, never. Oh, hey, we're all done. Lovely. 2 things associated with these notes for today are counting particles. It's literally just that. We need to like count electrons in ground state, in excited state, when it's an atom, when it's an ion, all that kind of great stuff. And of course, Lewis electron dot diagrams. Oh, these are sometimes called Lewis electron dot diagrams after Dr. Lewis, who came up with it, and sometimes they're just called electron dot diagrams or dot diagrams, because why would we only use one name for something? Yeah, so just practice doing electron dot diagrams, and they are just as simple as you think they are. So that is it for me for today. Thank you for learning. Thank you for writing the notes, and I will see you next time I'm looking at you. Hope you all have a great day.